200?
No. I technically am going to use more than 200, but I haven't explained why just yet.
Or you said that it thinks there's any 2,000 because that's how many points
I think it's 262.
Right. Per variable. That's how many subject data points there are.
Yep. So n is 2062.
Yeah.
And our chi-square right now is, I just had it and I forgot it. 40.212. So that's what it thinks it is. Now, I can actually calculate the discrepancy function. The discrepancy function is always, sorry, the chi-square is, this equals f times n minus 1. So if I divide this value by 1 less than the sample size, I actually get my FML. All right, so let me walk through what I just did here. All right, so this is the sample size, 2062. The chi-square is 48.212. So again, I'm just taking that from the output here, and we have the sample size reported up here. Now, technically, though, this is actually running. Oh, I'm sorry, I forgot one other thing. The other thing I need here is the degrees of freedom, and the degrees of freedom were 4. It was until we changed the.
Oh, okay.
Once we add that additional. Yep. Once we add that additional covariance, yeah, we lose 1 degree of freedom.
And FML is equal to f times n minus 1 divided by n. Is that what you said?
The chi-square divided. So this would be the chi-square divided by n minus 1. Oh, it didn't like the. There we go.
What's f notation?
That's the discrepancy function. ML is just the max. It's the maximum likelihood estimator. That's
okay.
That's the more complicated one from yesterday instead of the one we actually walked through the calculations. That was like a perfect little chaotic experiment there. All right. Sorry, I don't know what just happened there.
There we go.
Okay. All right, so let me zoom back in here on. All right, so. Let me zoom back out because something strange is happening. Didn't really want to force quit, but okay, I had a choice. All right, so again, this was, so again, chi. All right, so this was that divided by that sample size minus 1. And again, chi-square, just to confirm, the chi-square is actually equal to f times n minus 1. And f then, by consequence, would equal chi-square. Let me do chi-square divided by n minus 1. So that's the fit function that it calculated. Now, I want a significant value. I'm sorry. I want a non-significant value. So that means I need a chi-square that is, so what's the worst chi-square I could have with 4 degrees of freedom? It would be chi-square inv, is that right? Chi-square inv.
I think there's a dot between the Q and the I and V.
Yeah, that's the, so chi in, there we go, chi in. I want a chi in of 0.05, and I want 4 degrees of freedom. So that says, okay, that says if I had a chi-square value of 9.4877, then I actually would have a 0.05, and anything below 9.4877 would actually give me a p-value less than 0.05, p-value greater than 0.05, and I'd fail to reject.
Wait, sorry, we want it to be, so if our chi-square were 9.48,
yep,
we would have 0.05,
p equals 0.05,
which would still mean reject.
Well, no, it'd be right on the boundary.
Yeah, okay.
Yep, so puts us right on the boundary of rejecting.
Less than 9, if we had a chi-square less than 9.48, we would
Fail to reject. Exactly. Let me actually put that here. So in other words, so the smallest p-value would be 0.05. So this is actually using that smallest p-value. Okay, so the worst chi-square. So if we have any larger p-value, if we have a larger p-value, so I'll say because a larger p-value means fail to reject. Fail to reject the null. So any chi-square less than this means fail to reject. All right, so I'm going to do one more calculation then. If I take this formula here, I could rewrite it yet one other way. What does my sample size equal? Well, technically my sample size would equal chi-square divided by f plus 1. So I'm just going to do that. I'm going to take the chi-square that I want, divide it by my f value, and add 1.
So 0.023 plus 1 on the bottom.
Yep.
So like 1.0.
Yep, so this is 0.0233. Oh, I'm sorry, no. This is the worst chi-square I want, 9.48 and change. I'm going to divide it by 0.023, my discrepancy function, and then I'll add 1. So this says if I had had a sample size of 406, my chi-square value would have actually been below the cutoff. It wouldn't have been in the critical region.
So we talked in my other class about how you could run this just putting in a covariance variance matrix.
Yep.
But when you do that, do you have to tell it a sample size?
You have to, all the programs require a sample size as well.
Okay.
Yep.
And theoretically, you're putting in your actual sample size.
Yes. Yeah, exactly. Yep.
Okay.
Now, there's a name for the calculation I'm doing here.
Okay.
There actually is. So let me show you. So if n had been 50, the chi-square value would have been the f function times 50 minus 1. And that p-value would have been chi-dist, that 4 degrees, 0.08. If it had been 150, sorry, what did I want to do? I wanted to do, yeah. Let's just do it like that. Okay. So look at my sample sizes here. If I had run this and I had only had 100 points, my chi-square value would have been 2.315 and change with a p-value of 0.677. Clearly, I'm not going to reject with that p-value. I could have even gone up to a sample of 400 and gotten 933. My p-value would have been 0.053. Still above 0.05. I failed to reject. The best I could have done was 406. At 406, I'm still just going to clear it, barely. .0502, and at 407, I'm probably not going to clear it. So at 407, so this is my brain just, the name of the I can even see it in the output. Oh my gosh. Hmin, the Hostapler. Oh my goodness. Okay, this value, 406, has a special name. It is the lowest sample size that you could have obtained. I'm sorry, I said that wrong. Largest sample size that you could have obtained with your sample covariance matrix. If you had a sample of 406 that had the same variance covariance matrix as you have, then you would actually have gotten, a non-significant p-value, and you would have failed to reject the covariance-variance structure hypothesis.